So this is the seventh, I think, video in my series of videos on Georg Cantor's contributions to the founding of the theory of transfinite numbers. In this video, I'm just going to continue with what I started in the last video, really, which is looking at this second number class of ordinal numbers. So here we're looking at the second number class in general, the actual aggregate itself, and determining some properties relating to that particular aggregate. But in the rest of the videos that I'm going to be making, we'll be looking more at specific types of number from the second number class, as opposed to just the aggregate as a whole, really. So the first theorem here, Theorem 16a. So this video's roughly corresponding with the stuff from section 16 in Cantor's work. The totality of all numbers alpha of the second number class forms, when arranged in order of magnitude, a well-ordered aggregate. So I'm not going to prove this, but we have already kind of remarked that the second number class is a simply ordered aggregate, but this theorem would actually confirm that it is a well-ordered aggregate as well. And then from that, theorems B and C, they're fairly straightforward conclusions that we can make, really. That every totality of numbers of the first and second number classes has a least number. So in other words, every kind of partial aggregate of the second number class, or the first and second number class, with this being a well-ordered aggregate, then every part of a well-ordered aggregate has a least element, a least number. That's something that's been shown or stated at least as a theorem in one of my previous videos. And every such totality, so in other words, every totality of numbers from the first and second number classes, when arranged in order of magnitude, also forms a well-ordered aggregate. Okay, so Theorem 16d, which I am going to prove, says that the power of the second number class, of all numbers of the second number class, is not equal to Aleph naught. So we're going to go for a contradiction with this, a proof by contradiction, and we're going to assume that the power of our aggregate of all numbers of the second number class is actually equal to Aleph naught, and from this we'd hope to get our contradiction. Well, if that's the case, then I can bring this aggregate into the form of an aggregate that has the type, the ordinal number omega. So effectively gamma 1, gamma 2, gamma nu, etc., where gamma nu precedes gamma nu plus 1. Notice that I'm not saying that gamma nu is less than gamma nu plus 1. I can't say that, because to get from here to here, all of the elements of the second number class which are in here are in this sequence somewhere, but I've had to break up the original order. So this was arranged in order of magnitude. This is just some other ordering that I've placed now between the elements. So it is a simple ordering, but it's not determined by the magnitudes of the actual numbers in there. So then what we're going to do is we're going to start with gamma 1, and we're going to go along this series until we get to the least index row 2, such that gamma row 2 is greater than gamma 1. And then we're going to go along again until we get to the least index gamma row 3, such that gamma row 3 is greater than gamma row 2, which in turn is greater than gamma 1, and continue this process. Gamma row nu, etc. And also it's going to follow that 1 is less than row 2, is less than row 3, less than row nu. So this means that I've got a fundamental series here, a fundamental series of numbers from the second number class. So by what I proved in the last video, there's going to be a limit to this, a definite ordinal number that we can call the limit of this, which we'll call gamma. And this limit number is itself going to be a number in the second number class, and it's going to be the next greatest after all of the gamma rho nus. Okay, so that's one of the theorems that I proved in the previous video. But now notice that for each nu, gamma rho nu is going to be greater than or equal to gamma nu. Okay, just because of the way that the terms are selected from this sequence here. So if gamma is greater than all of these rho nus, so gamma is greater than gamma rho nu for all rho nu, then gamma must be greater than every gamma nu, using this the transitivity effectively of this series of inequalities to get this. But now this aggregate, it does contain all of the elements of the second number class. So because we know that gamma, the limit ordinal of a sequence of numbers from the second number class is itself a number from the second number class, then actually gamma must be in there somewhere. It must be in this second number class, and therefore it must be equal to some gamma nu naught. But this is a contradiction, because we've already established that gamma must be greater than all of the gamma nu. All of the numbers of the second number class are accounted for in here, and we've said that gamma is actually greater than all of them. But now we're actually saying that gamma is equal to one of them. Well, that's the contradiction. So therefore, what we can say is that the cardinal number of our aggregate, the aggregate of all of the numbers of the second number class, cannot be equal to Aleph naught. So alpha is not equal to Aleph naught. So it remains to be seen what the cardinality, what the cardinal number of this aggregate actually is, but what we can say, it's not equal to Aleph naught. Okay, so here we go with the last two theorems from this section. So theorem E, any totality beta of different numbers of the second number class has, if it is infinite, either the cardinal number Aleph naught or that of the second number class, which we've just proved in the previous theorem is not equal. The power of this aggregate is not equal to Aleph naught. It still remains to be seen what the power of this aggregate is, but that's where the next theorem comes in. The power of the second number class is the second greatest cardinal, Aleph 1. So this, let's say that between Aleph naught and the power of this aggregate, or the cardinal number of this aggregate, there is another cardinal, A. Then there must be some kind of partial aggregate of this, made up of numbers beta, such that the power of this partial aggregate is equal to A. Now, because this is the aggregate of all of the numbers from the second number class, then any partial aggregate must be an aggregate of numbers from the second number class as well. Well, if that's the case, then using this theorem up here, totality of different numbers of the second number class, if it is infinite, either has the cardinal Aleph naught or that of the cardinal number of the second number class itself. So, okay, we're not really interested if it's finite, so let's assume that it's infinite. Then either the power of this aggregate is equal to Lf naught, or the power is equal to the power of the second number class. So in other words, there is no cardinal number in between Lf naught and the power or the cardinal number of the second number class. So naturally this is what we call Lf1. So the second greatest cardinal is Lf1, and in quite a natural way, so this is something that's actually not proved explicitly in Cantor's work, but we can get a nice sequence of cardinals, Lf2, etc., Lf nu. But these wouldn't, just with finite subscripts here, that wouldn't itself exhaust all of the possibilities. We could get onto Lf omega plus 1, etc., etc. So we could have Lf with any ordinal number as a subscript, effectively. But the thing is that there is nothing in between Lf naught and Lf1. That's the main point, really, of this theorem. So that finishes up with section 16 here. The next part of Cantor's work really concentrates on specific types of number from the second number class. So rather than looking at numbers, the second number class in general, and just talking about general numbers in there or the aggregate itself, we're going to pick out particular types, forms of numbers in there, and investigate some of their properties. So that's the end of this video. It's been quite a short video, but I want to thank you for watching it, and I look forward to seeing you in the next video.